app servers. So this is going to be about immutability in JavaScript. I'll try to explain to you what immutability is, in case you don't know, why it's useful, and what we can use it for, and how to use it in JavaScript. And some use cases where it's particularly interesting in JavaScript. My name is Christian Johansen. I work for Kodemarked, which is a consultancy based here in Oslo. And currently I'm at the NRK, the Norwegian Broadcasting Company, doing JavaScript things. So I'm going to start this talk with something that I'm not entirely sure if it's true, but it's a theory of mine, so I'll present it. And that is that so over the last few years, many functional programming patterns have emerged into the JavaScript community one by one, and the latest one to gain widespread adoption is immutability. And I think that it came to JavaScript via Clojure. Who has heard of Clojure before? Right, everyone. So it's a Lisp that runs on the JVM, and its most compelling feature is a rich set of immutable data structures and really, really good APIs to work with them. There's a guy called David Nolan. Who's heard of David Nolan? Hey. He wrote a Clojure compiler that outputs JavaScript, which is called Clojure script. And that basically gives you all the APIs and data types from Clojure in JavaScript. And then he sat down and looked, how can I build UIs with this tool? So he discovered Facebook's React library. And then he wrote a library in Clojure script called Ohm, which basically combined immutable data structures from Clojure with React for rendering. And he achieved some really nice things. One of the things he did achieve was that he outperformed React in a framework that is wrapping React in a language that compiles to JavaScript, which sounds really weird. And hopefully through this talk, I'll be able to explain to you how he did that. So to everyone who's standing over here, there's lots of chairs over here. OK, so that's my theory that immutability came to JavaScript via Clojure. So first, I want to start by defining what immutability is. And I'll do that by defining mutability first. So when you have a piece of data that's mutable, it means that it can change. So you'll have an object or an array or whatever. And at some later point, that same reference may point to a different value, or partly different value. So immutable values never change. You can initialize them, then you have a piece of data, and you can never, ever change it again. The only thing you can do is to read it back. And if you want a new piece of data, you can base it on the previous one, but you have to create new ones all the time. So this might seem impractical, but let's consider some examples that I'm sure you are familiar with. So numbers. You have a 2 and a 3, and you add them together, and you get the number 5 back. Now, doing this does not change the meaning of 2 or 3. It just gives you a new value. And similarly, let's say that I had objects that represented these numbers, a big int or whatever, and then I performed the add operation. Now, what is the value of A? Your answer to this question will depend on your previous experience or if you know any APIs that look like this, but basically with typical object-oriented software, you wouldn't know. Maybe A is now a big int representing 5. Maybe it returned a new one, so it still represents 2. We don't know. We would have to look up the documentation. But that would be preposterous if that was the case for numbers. If you add 2 numbers together, you cannot never, ever use the original ones again. That doesn't make any sense. Another example is strings. So here I have a string, and then I want to get an uppercase version of that string. So I call the toUppercase function, which sounds kind of scary. Sounds like it's going to change the string. And it does give me back a string that is changed, but the original string is still around. Yay. So we have a value, strings, that is in fact immutable in JavaScript and in most other languages. I think everyone I've worked with, except for maybe C, where there's no strings. But Strings are immutable in most languages, and numbers are as well. And we're used to working with them as immutable, even if you're not used to thinking about them as immutable. It's just the way they are. So let's say I have an array, then I push a value onto the array. Now the question is, what is v2? If it would follow the semantics from strings and numbers, it would be an array containing the number 2. But instead it is, does anyone know? It's 1. What does that mean? That is the new length of the mutated array. So the array, the original array, the empty array, is now gone. We can never ever find it again. And the original array has changed into something containing a 2, and the operation returned the new length. Okay. Let's instead imagine that we had immutable arrays that would work just like strings and numbers. In that case, we would initialize it with the immutable array function or whatever, and then when you call push, it has to behave differently than for arrays, because as I said, immutable values can never change. So instead of changing the original array in this case, push will now return a new array that contains all the numbers. And then I also have the old array with just the first 4. And you might wonder, why is this useful? Well, this allows me to decide when we lose data. So when you have mutable data types, data loss is built in. Whenever you want to update or change something, you lose the previous state. And if you want to keep it around, you have to manually perform deep copies of everything. With immutable values, that doesn't happen by default. We could, of course, decide to discard the old one, but we have them both available if we need them. Let's expand this into objects, as they're called in JavaScript, or maps, as we know them in many other languages. We could have immutable maps to create a piece of data representing a person. Then that person celebrates their birthday. And that doesn't remove the fact that that person used to be 1 year younger. So now we have both references. And if we're not interested in keeping both around, we could just overwrite the reference. We could reuse the same reference, and I still have the option to lose data, just like in the good old days. But in the cases where I want to keep the old data, I have that option as well. So my argument is that immutability is inherently less complex than mutability, because mutable data types, they couple state with time. So when you have a mutable piece of data and you access it several times with some time elapsed in between, you will never know what to get back. When you have an immutable piece of data, you will always have the same thing. And this is useful for several applications. And one of them is to create UIs, generally. In this specific case, it's going to be a game with bombs. So I'm going to show you some pieces of this application which I wrote with immutable data. So we're going to look at how the game model is built up and how the core logic is built up, and we're going to take a look at how the UI is built up and how immutable data types work through this app. But first, JavaScript doesn't have any built-in immutable types, unfortunately. Maybe we'll get them later, but as of now, we don't have any useful immutable data types. So we'd have to use a library of some sort. And right now, there's 2 popular immutability libraries for JavaScript, and I'm sure there's a whole bunch of other ones as well. But Mori is probably the first one that was widely known. It's also written by David Nolan, and this is actually the data structure implementation used in ClojureScript, except it also has a JavaScript API, so you can use it from JavaScript. This is not the one I'm going to show you now. Mori implements Clojure's APIs, and the other one that I'm going to show you, Immutable JS, has an API which is more similar to what you would be familiar with, which is JavaScript arrays and objects. So that's why I'm using this one, but you should totally check out Mori after the talk. So Immutable is written by a guy at Facebook, and they are pushing it rather heavily along with React and the other things that they're doing now. So I'll show you 2 interesting parts from the core of the game. And the first one is the create game function because it's interesting because it defines a data structure for the whole game. So typically when you are working with immutable values, you would not create custom classes to hold your data. And the reason for this is that if you would create custom classes to hold your data, you would have to either subclass an immutable type or re-implement lots of methods to kind of get that behavior from the libraries. So instead, we're going to operate on raw data, and we keep all the functionality on the side. It's called functional programming. So create game simply returns a map that describes the current state of the game. And it has some columns, it has some rows, and most importantly, it has some tiles. So I'm not going to show you that. I will. And then we have a bunch of mines. So you initiate the game by telling it how wide and how tall and how many mines in that game. And the tiles is going to be a list of tiles where each tile is a map describing that tile. And it looks like this. So we have an immutable list of immutable maps. Each map represents a single tile, and it only has two pieces of information. Is this tile revealed? Which means has the user clicked to open it? And does it contain a mine? That's the only piece of information that the tiles are storing right now. So this function would have to create a random game and place the mines all around. I'm not going to show you that. Just want you to see the structure. But this is currently returning a JavaScript object. So we want to make it into an immutable map. Well, then you simply wrap it in immutable.map. And that gives you back an immutable map with these properties. So that's the create game function. Let's see what it's like working with this data in reveal tile, which is perhaps the most important function in all the game. So whenever you click one of the boxes on the page, we have to uncover that tile, and we also possibly have to uncover more tiles around. If you hit a mine, we're going to lose the game. Pretty much all the logic of the game resides inside reveal tile. So this reveal tile is not a method on an object. It's a function that accepts a game as its first argument. And the second argument is the tile index, which tile to reveal. And this function will return a new version of that game with that tile revealed. So you can see where I'm going with this. Just like we had when you add two numbers together, you get a new number back. When you take a game and you do affected state somehow, you get a new game back. And then you can choose what to do with the old one. And I'll show you some examples for that later. So the first thing, let's say that these were immutable. So I'd have game.tiles tile is revealed. This is how you would do it if the game was mutable. But it's not mutable, so I cannot do this. Instead, I'll have to get the tiles, and I'm going to have to get the tile, and then we're going to have to set is revealed. Pretty cumbersome. And what does this do? This obviously cannot change the tile because the tile is immutable. So it returns a updated tile. Great. Now what do? I'm going to have to go ahead and get the tiles again and then set the tile to be the updated tile. This returns updated tiles. So then we're going to have to set the tiles as well to the updated tiles. And this gives me a new game which I can return. Whew. That's a lot of code for a small, tiny flag. So, of course, we don't have to do all this, but this is conceptually how it works. You can do this if you want, but I wouldn't recommend it. What we can do instead is that we can call game_setIn, which is a abstraction that's designed to do this kind of thing, to set a piece of data deeply inside some immutable structure. So you pass in basically a path, tiles, tile is revealed, and you set that to true. And this will return a new game. So long, suckers. So it's almost as short as the original mutable version. But now we have a reveal tile which deals with immutable games in and out. Good. There's one thing you should be aware of with this one. So because it's designed to put values into a deeply nested structure, it's null tolerant. So let's say that this game doesn't have any tiles. This function is just going to create placeholders and put values in them. So we should check that. Let's see. We can use getIn, which is this getter version of that same thing. So we want to check that the tile actually exists. So we don't allow users to reveal tiles that doesn't exist on the board. So if the tile does not exist, then we will just return the old game because there was no state change. We could, of course, throw an exception or be assholes, but it doesn't do us any good, so we'll just return the game instead. Fine, so this is my reveal tile. The finished version is a bit longer because we have to make all kinds of arrangements. If there are no mines nearby this cell, then we will want to reveal the surrounding tiles and all kinds of rules. So I'm not going to do all that, but this is basically what it's like working with immutable maps and lists instead of mutable objects and arrays in JavaScript. Okay. So let me show you something. This is basically the data structure we're operating on. Can you see that? Or does it get swollen? Okay. So it has a bunch of mines. There's 9 cells here, and this represents a game that looks like this. 2 mines, and then some counters indicating how many nearby mines and so on. So conceptually, when you do this, set in, and then set the flag to true, you get a new data structure, the one on the right-hand side, which is almost exactly the same. But conceptually, we had to copy everything over to the new one. But if we were to do that, that would be really inefficient. We would use a lot of memory, and it would also be slow in terms of CPU usage. So the only difference between these two is this one tile that changed. It got a Boolean flag set on it. Now, the interesting thing is that all the other tiles are immutable, so they can never change, which means it's completely safe for these 2 versions of the game to actually share those. So when you use a library like Immutable JS, or if you use Clojure or whatever, this is what's actually happening. You get a new immutable copy, which is mostly just pointing to existing data in the previous structure. So you could call reveal tile 10 times, and the amount of memory you would use would be roughly the same as 1 times the data and a few small diffs, instead of duplicating the entire data structure 10 times. This is pretty important, and this is part of the reason why this actually works as well as it does. And this is called structural sharing. I'm not going to go into it in more detail than I just did, but if you're interested in this, one place to start would be this talk from ReactConf, where the author of Immutable JS goes into detail about how he implemented structural sharing in that library. And you'll also find references to Rich Hickey, who implemented Clojure, where he talks about how it works there. So it's really exciting stuff, but it's outside the scope of this talk. Okay, let's check out how this affects our UIs. So we're going to want to use immutable values in the UI. And this game of mine is rendered with React.js. So how many has used React.js? Okay, quite a few. I'll show you quickly how it works, but let's see. If you haven't used it before, hopefully you'll be able to follow along. So in React, you define components that you can render. And you do it in a quite cumbersome way. Create class like this, and then you have a render method which should return some other components. And you can return a H1 component, which will render as an H1 element on screen. Hello, and then it can have some data tucked away in this.props. And to use it, we need some data. Name, Java zone, and then React.render, and then we instantiate our component with data, and we render it into an element in the DOM. That's basically the quickest React 101 you can get. Okay, yay. we have text on the screen. So the problem is that if I'm using an immutable map instead, this no longer works like it used to. And the reason, of course, is that the immutable map does not expose its properties via raw property access. You have to use the get function, like I showed you before. So something like this. Get name. So now our text disappeared, which is a neat feature. Turns out that I got a type error. This.props.get is not a function. Okay, so what's happening is that React treats whatever is sent in here as a mutable object, or it doesn't actually have to be mutable, but it treats it as a collection of properties, and instead of just using the object, it picks all the properties out of there and sticks it into some internal state management thing. So it's not safe to pass immutable values on like the upper level of React components, which is a bit annoying, but we can work around it. And we can work around it by wrapping it in an object. Now React will pick the data property and stick it somewhere else and then eventually give it to me. So I can say props.data.getName, and now I can use immutable values in the UI. So usually I work around this inconvenience with a small abstraction, which I usually call create component. And then components can have lots of functions implemented. Usually I only implement the render function, so I made it so I can just do this. And I also like to get my data passed in arguments. So you can create a 10-line function that gives you this instead of the React API if you want. Didn't work. Yeah, because I also fixed this. Okay. So that's the small caveat. If you're using immutable objects, you have to make sure that React doesn't try to pick it apart. So wrap it in an object. So let's get over to the actual game, which currently looks like this. And I'm going to show you what it's like to render a single tile. So here's the current version of the tile. It just says tile. So it should be a div. It should have a class of tile, and it should not have any text, at least not initially. That gives me a bunch of squares, which is a little bit better. This function is going to have to fork because a tile can be in one of two states. Either it has been revealed or it hasn't. So we're going to have to get our data, and it's stuck in that props.data like before. I'm just going to do this because tile reads better than this.props.data. So if tile get is revealed, and this is just like working with regular objects, except that instead of dotting onto a property, you say tile.get. If it is not revealed, it's going to have another div inside, which is called the lid. Not the lib, but the lid. So it looks like this. So now it looks like a complete game, except it doesn't do anything. So next up, we're going to have to give that the concealed one needs to get a click handler to reveal the cell, or the tile, sorry. So there's in this file, this is a bigger file that I'm showing you, there's something called actions available, and I can emit messages on it, tell it to reveal the tile with this ID. And what happens now is that someone else is going to call that reveal tile function that I showed you before. It will get a new game back, and it's going to call React render over again with that new version, and we'll get the updated version on screen. Yay. So clearly some information is lacking, but you can see that it's functionally on the way, at least. All right, so we need to put some more information in here. We'll use tile get, I think it's called threat count, which tells us how many nearby mines there are. Yay. So the mines don't look very threatening right now. They're just blank. We can fix that as well. And that's just a matter of adding stuff to the class name. So if it is a mine, it will get the class name mine added. Otherwise, nothing. And also, you can see all the zeros here. They usually don't appear because they're just adding noise and no information. So we can say that if there's more than 0 mines, we'll display them. Otherwise, we'll display nothing. OK. That is basically, oh, come on. I suck at Minesweeper. OK, so that's the basic gist of the UI. Now, I didn't say much about how React actually renders this. So let me try to explain it to you. So the first thing that happens is that we create a game, and I tell React to render it. And it's going to invoke this tile component for every tile in the game, which in this case is 256 times. Now, when I click this one, only one tile changed. And what React is going to do now, because we called the reveal tile function, we got a new game back, and then we told React to render that new game, then React is going to go through all the 256 tiles over again and say, here's some data, please render yourself. And then, before React draws this on screen, it's going to compare to the previous version and figure out that, hey, only this cell changed. So the other ones are not going to get drawn over again. Only this one gets drawn. And this always happens. But we can improve on this because even if this is the only one that changed, React actually told all these other ones to render the components, which create something called a virtual DOM. So everyone is being rendered in memory, but only one is being rendered on screen. Now, React has this hook that allows us to influence how it decides whether or not something needs to render. It's called shouldComponentUpdate. So if this function returns false, it basically tells React that it should not ask this component to render at all, not even to the virtual DOM. And doing so is pretty stupid because you don't get any updates, right? You get the initial render and then nothing more happens. You can't really see it on screen, but I'm clicking all these tiles and nothing is happening. So returning false is no good. But we know more than React about our data. So usually when you have mutable data, you'll get some new mutable data here, and you can compare them to your existing mutable data. The problem is that if you want to do that, you have to do a deep compare of two objects that are potentially large, and the whole thing would become really painfully slow. So that's why React doesn't do that for you. But when you're using immutable objects, we can do this. Because I know that if a tile didn't change, it's still going to be the same object. And reference equality checks are really cheap. And they are more cheap than doing all of this crap just to figure out that, hey, it didn't change after all. So you can't really see it, but it's really a lot faster now than it used to be. So it doesn't really matter for this game, but if you have a large, complicated UI, it is going to matter. So this thing now renders about 3 times as fast as it used to be, which gives me a lot of room to add more of complex Minesweeper features. Whoa. OK. So I made a small test to check this out. So I wrote this game 3 ways, with mutable data, and then with immutable data, and then finally I added the shouldComponentUpdate fix to the immutable version. So the mutable one took, on average, 871 milliseconds to do what? So I created a loop that goes through all the cells that didn't contain mines and then tell them to reveal. This will cause the maximum amount of renders for a game. So just it stands there churning for a second and then shows you the game completed. So with mutable data, that took about 871 milliseconds. The actual number is not interesting at all. Then I did it with my immutable version, which is horribly slow. It was 3 times slower. And this is not surprising, really, because the set-in and get-in functions are more computationally costly than just looking at properties on objects. So we are using a more complicated abstraction, so it's not surprising that it's slower. But then I added the shouldComponentUpdate fix, and now I'm faster than the mutable version. And really the whole point of this slide is to tell you that if you were to decide on data types with micro benchmarks, you would never use immutable data types. But immutable data types enable a whole class of optimizations in my rendering code that would not be possible with mutable data types, so I end up on the faster side after all. So this just goes to show that we can use better abstractions, even if they're more costly on the unit level, and still end up with good performance on the whole. And this is how David Nolan managed to outcompete React by wrapping it in another framework, in another language that compiles to JavaScript. It's the power of immutability. So the good thing is that we now don't have to, or I'm not sure if that's a good thing, but you can now get the same thing without having to use Clojure. It's going to be even better if you use Clojure, but you can get it in pure JavaScript as well. So one final note, that's the performance part of it. So by using immutable values, I also get to do other cool things. So because I can choose to keep around old versions of the game, things like undo or snapshotting is really simple to implement. Because I can just keep a record of all the old versions of the game, and if you want to go back, I can let you go back. So that's what we're going to do now. I'll have a, we'll render an undo button into the game, undo, and we'll add the undo button to the game. Okay, here's the game again, and there's a malplaced button that doesn't look like a button down here. It doesn't do anything, but there's a button there. So when you click that button, we are going to send a message just like we did before. Actions, emit, undo. And this doesn't need any arguments. Undo just means revert one step, please. And clicking around, the button still doesn't do anything. We're going to have to implement it. So here, it says to do, undo. So here you can see how this is working. I create a game, and then when you say reveal, I check if the game is over, blah, blah, blah. And then I just create a new game instance and overwrite my previous, or my reference. So what I want to do now is I need to keep the previous version. Actually, I need to keep the previous versions. So we'll create a immutable list to hold those. It doesn't have to be immutable, but so, and then game history. So before we overwrite the reference, I am going to push the previous state of the game onto the history. And this doesn't update the list because it's immutable. It returns a new version of the list. Now, I do not need to keep the old game history around. That would give me a history of game histories, which would be really confusing. Anyway, so now we keep them around, and then we can answer to undo. So when the undo message comes in, first thing I have to do is to check if we have any history to undo to. So the size needs to be bigger than 0. Actually, if it is 0, we'll just abort. If there is no history, that means that you're on the initial state, and I cannot help you any further. And then I'm going to set the game to the previous version of the game. And then we're going to set the game history. We're going to drop that last one, and then we'll call render. So now I keep a reference to all the games as we go along, and if you hit undo, I'll just reinstate the previous one as the current one and render. And now we have the easiest Minesweeper in the world. Ooh! I'll just hit undo. Thank you. Arguably, this game doesn't need an undo feature, but maybe you want to create a game that does. Anyway, I think that this just goes to show that because we have chosen a data structure that doesn't have data loss built in, doing something like this becomes trivial. If you were to do this with a mutable data structure, it would not be trivial. It might not even be possible without severely reorganizing your code. Another interesting feature in this related to this is snapshotting, where you could basically allow someone to take a snapshot of the app, the current state. You could use it for bug reporting. Let's say that something bad happens. You can add a button that just grabs the current state and sends it to you. You could load it up on your machine and see the app in the exact same state as your user saw it. I saw someone implemented a pixel editor thing where you can draw pixels, and their undo and replay made a lot of sense. And he made an animated GIF export using the history of the game, just by taking each and every state of the game and playing them as individual frames. Anyway, immutable data types offers you lots of flexibility to do these kinds of things. Oh, there's my slide. So if you want to dive deeper into some of this, I wrote 2 articles recently-ish about immutability for SitePoint, which you'll find here. Then there's also the GitHub repo on the top, which includes the full source to the Minesweeper game, both with mutable data and immutable data, and some instructions on how to run the benchmarks so you can see for yourself. You can play around with the code base. And that's pretty much it. Any questions? No questions? Okay. Yeah? Mm-hmm.
What happens if you override the reference in this new immutable? Override the original.
Okay, so I have an immutable piece of data, and I make some change, which gives me a new one, pointing back basically to the old one. What happens if we change the reference to the old one? Nothing. It doesn't actually point to the original one. They share data in a shared place. So if you remove the first reference, you remove the first reference, but the data is still being referred to, so it's not being garbage collected or anything. The thing you have to look out for is that if you put mutable data into the immutable data structures, then you're screwed. So an immutable piece of data is only as immutable as its most mutablest member. So basically, if you want immutability, everything has to be immutable. As soon as you put something mutable in there, it can change, and then all the other references downstream are screwed. All bets are off. All right? I will be at the Kodemake stand now if anyone wants to come talk. And oh, I forgot to mention, I have a talk tomorrow as well. So if you like this, you should come see it. If you didn't like this, you should give me a second chance. It's 1 o'clock in room 1, and it's going to be about new features in JavaScript. Right, have a good night.